Okay, in this video I would like to just go through two questions from the textbook that I set you for your homework, just to really give you some support with this, because some of these questions are quite tricky. So hopefully you've done these questions already, and now I'll show you how I'm going to do them, and you can compare your answers and your methods. So, question 2. A student pushes a trolley of weight 150 newtons up a slope of length 20 meters. The slope is 1.2 meters high. Calculate the gravitational potential energy gained by the trolley. Okay, so for this you're going to need the formula gravitational potential energy equals mgh, and we want to know the gravitational potential energy, so we need to know mg and h. So we need to identify these things. Firstly, I'm going to identify the height, the change in height, because I can see it right in front of me. So the change in height is always the change in vertical height, which is 1.2 meters in this case. So that's what we're going to put in there. However, they haven't told us g, and they always tell you g if you need to know it. They haven't told us g. And have they told us m, the mass? Well, no, they haven't, because mass is measured in kilograms. They've actually told us the weight in newtons, which is 150 newtons. So they haven't told us m or g, they've told us m times g, because m times g is the weight. So we know that all of that, m times g, is 150 newtons. So 150 newtons times 1.2 meters is going to be the gain in gravitational potential energy. So this is really important. A lot of people would not notice that this is in newtons and accidentally put that 150 newtons in as the mass, but that's not the mass, that's the weight already, the mass times g. So now we just need a calculator. So we've got 150 newtons times 1.2 meters is 180 joules apparently of gravitational potential energy gained. Lovely. Okay. They pushed the trolley up the slope with a force of 11 newtons. Show that the work done was 220 joules. Right. So now we need the formula. Work done is force times distance moved in the direction of the force. Now, the force we're interested in is in this direction, and the distance moved in that direction is this distance here. So you've got to select the right numbers. So here the force is going to be 11 newtons times the distance moved in the direction of that force, which is 20 meters. So it's not the height in this case. That we don't even really need a calculator for. Times it by 2 is 22. Times it by 10, 220 joules, as they've asked us for. So we've shown that the work done by that force is 220 joules. However, notice that we haven't got 220 joules 220 joules of gravitational potential energy gained. So this much energy, 220, has been transferred by the force, but only 180 of that has gone into gravitational potential energy. Where could the rest have gone? Let's find out. Now, if the student pushed the trolley up the slope at a constant speed, explain why all the work done by the student was not transferred to the trolley as gravitational potential energy. So we've basically got 40 joules missing. Okay, where's the energy gone to? Well, whatever the source of energy was that was pushing it up, in this case I guess it's whatever the student ate for lunch or something like that, has gone to GPE, gravitational potential energy, plus what else? Some of it must have gone somewhere else. Well, it hasn't gone to kinetic, because they've said very specifically that this was done at a constant speed. So if there's no change in speed, there's no change in kinetic energy. So none of this energy has gone into kinetic energy. It hasn't sped up. So the only other place for it to go is heat, due to friction, because there's going to be friction within the bearings of these wheels, there's going to be friction, there's going to be resistive forces, and that transfers energy to heat. So in answer to that question, I would say there were frictional forces or resistive forces, which meant that some of the energy, 40 joules you could even say, well, sorry, I've gone too far. So we had 180 joules and 220. So 40 joules has gone missing. So it doesn't tell you here. This isn't an exam question, but if it was an exam question and it told you how many marks, I'd be looking at the number of marks and thinking, what do I need to say here? If it's just 2 marks, I'd say, you know, energy is transferred to heat because of friction. If it was 3 marks or 4 marks, I'd be like, oh, okay, do I need to say a bit more? Maybe I need to say that how much energy or something. So think about, for exam questions, think about how many marks are available. Here, 40 joules of energy has been transferred to heat because of friction or resistive forces. So hopefully that's cleared up that question. The key thing really, 2 things. One is identifying which distance is the distance you want. The other one in this case was spotting that they'd given you the weight and not the mass. Okay, now look, I've just looked at this next question and it's a bit of a strange one, alright, but you know, we'll just go with it since I've set it. So, a parachutist of total mass, I guess that includes the parachute, 75 kilograms, jumps from an aeroplane moving at a speed of 60 meters per second at a height of 900 meters above the ground. Calculate her kinetic energy when she left the aeroplane. Now, I imagine the aeroplane's flying horizontally. It doesn't actually say this. Okay, so the moment she leaves the aeroplane, this is her, I'm going to make her into a blob. She's 75 kilograms and she's moving at 60 meters per second. I mean, I'm imagining it's horizontal. I imagine the plane's traveling horizontally. So the instant she leaves the plane, she's moving with the plane, she's moving at that. So I think that's what it's asking for. I don't know. Now, what's the formula for kinetic energy? Is a half mv squared. So it's going to be a half times 75 kilograms times 60 meters per second. Now you've got to remember that whole thing there. The 60 gets squared but nothing else. So we're not going to square the whole lot. We're just going to square the 60 meters per second. But don't write it, what I wouldn't write it as, you see I wrote those brackets, I wouldn't write it like this because that's just ambiguous. That almost looks like an acceleration and it looks like that's a unit there when you put the squared without the brackets. So I like to chuck the brackets in just so it's clear what we're squaring. We're squaring 60 meters per second. So let's chuck this in the, wrong button, sorry about that. Let's chuck this in the calculator. So we've got 0.5 times, oh, let's just clear all this stuff out of the way there. Clear. 0.5, what have I done there? I've done it wrong. 0.5 times 75 kilograms times 60 squared. You don't need to use the brackets when we're doing it on here. Go. Wow, quite a lot. 135,000 joules. Which is also known as 135 kilojoules, if you like. I mean, I wouldn't bother doing that in an exam, but if you want to, it's fine to do. You could even convert it to standard form if you like, but you know, at GCSE level, it's fine to leave it as the very first answer I gave. Good. Okay, that's that. Now, her parachute. So loads of stuff happens then. You know, then she falls out. I don't know when she opens the parachute, but whatever. She ends up falling at 5 meters per second. Calculate her kinetic energy at this speed. Okay, let's do that. So now she's going at 5 meters per second. So now EK is a half mv squared, which is a half times 75 times 5 squared. She's moving at 5 meters per second. I'm being a bit sloppy with the units here, but I want to get things done quick. So I always recommend you put the units into your answers. So 0.5 times 75 kilograms times 5 meters per second. All of that gets squared to 5 equals 937.5. Whoops. 937.5 joules, is that right? Is that what I just said? Let me just check. 937.5, that is what I said. Okay. There we go. Calculate her loss of gravitational potential energy as a result of the descent. Okay. Well, that's going to be mgh. Now, they haven't told you g in this, so I'm going to use 9.8 just because this is to, you know, the numbers are to 2 sig fig, so I'm going to use my version of g to 2 sig fig. If you use 10 for this, don't lose any sleep over it. Remember, in the exam they'll always tell you which version of g to use. So it's 900 meters change in height. So EP equals mgh, which is 75 kilograms times 9.8 newtons per kilogram times 900 meters. Let's chuck all that into a calculator. Clear all that out of the way. 75 times 9.8 times 900 is, wow, 661. I mean, I'm going to round this to like 3 significant figures. Well, no, I'll leave it. I mean, you know, we'll leave it. 661,500. No, I'm going to round it. I've rounded it to 3 sig fig instead of having it to 4 sig fig. Okay, so that's how much gravitational potential energy was lost. Okay. Calculate the work done by air resistance during her descent. So, this is tricky. Okay, you've got to think about what has happened. What were the energy transfers? Alright, so at the start she had both GPE and kinetic energy. She had GPE, gravitational potential energy, because a plane had lifted her 900 meters off the floor. So she had GPE because of that, and we've worked out it is 662,000 joules. 662,000 joules. Okay. Plus she had kinetic energy because the plane was moving horizontally at 60 meters per second. So she also had this amount, 135,000 joules because of the movement. Now at the end of it, she's got still a tiny amount of kinetic energy because she's moving at 5 meters per second. Where's all the rest of this energy gone? That's a minute amount of energy. Well, at the end of it, when she's just about to hit the ground, she's moving at 5 meters per second, and we've worked out that she's got basically, let's call it 1,000 joules, just to make it a nice round number. She's got 1,000 joules of kinetic energy. Well, how much energy did she have at the start? Loads more than that. What is it? If we add these two numbers together, it looks like 797,000 joules. Where's all this energy gone? All this gravitational potential energy that she got from being lifted up in the plane, and the kinetic energy, because the plane was moving at 60 meters per second. Where's it all gone? It's all gone to heat, basically, because of air resistance. So air resistance slowed down her horizontal motion, because she ended up falling basically vertically at the end of it. So her path would have been something like this, like she would have started off moving at 60 meters per second horizontally, but the air resistance would have slowed her down horizontally. So what's the question again? How much work has been done by air resistance during her descent? Well, all this missing energy has been air resistance, basically, has transferred it all to heat. So the air and her parachute would have got a minute amount warmer, a tiny amount hotter, because of all of this. So the air, the surroundings would be slightly warmer. Now how much energy is missing? Well, a lot, basically, because we've got 797,000 on one side minus only 1,000 accounted for, which leaves us 796,000 joules. That's how much energy is missing. That's how much energy has been transferred to heat by air resistance. So this is a funny question, a funny one. I haven't seen it before like this, where they've got you to consider the horizontal motion of the person as they leave the plane. Often that gets ignored. So often when you're doing skydivers, they ignore the fact that the skydiver actually has energy at the start, kinetic energy at the start. But this one they've included it, so it's nice that it's a more realistic problem. It just makes it unusual and unfamiliar to you, but you have to be able to deal with unfamiliar questions. So I'd say this is the answer. I haven't looked it up in the textbook answers to see if that's what it is, but I'm happy that this is the amount of missing energy, and all of that has gone to heat by air resistance. So hope the video has helped clear up these questions. This question here is totally standard question that, you know, it's just all about identifying which formula to use and what they've given you. This question here is a bit more unusual in that it gives a little bit more or an accurate picture of what's going on. So if you found this one tricky, don't worry about it too much. If you've got any questions, bring them to the lesson.